Hi, welcome to the second screencast of the day, this one about force versus distance graphs. I'm going to make this quicker than the other one, I promise. And the good news is force versus distance graphs are pretty easy to understand. They do come up a bit on the AP test, but that's good news because they're not hard. Let's get started. So I think every graph we've looked at up till now has had time as the x-axis, but in this case we're going to have distance as the x-axis. Now, we've done this a bunch this year where if we want to find the area under the curve, we integrate to find the area under the curve. We just multiply the y-axis by the x-axis values, right? But in this case, that's force times distance. Force times distance, isn't that what we just said is work? Yes, it is. So in this graph here, if I just integrate to find the area under the line, that tells me how much work was done on the object, how much its energy has changed. So in this case here, I have 200 newtons that are positive, and that means the work was applied in its direction of motion, in the positive direction. We always assume the initial direction was positive, so therefore work in that direction is going to do positive work. So I have 200 times 8, that's 1,600 joules of positive work. So let's just say the object in question initially had 400 joules of kinetic energy to start with. Well, now I've just done 600 joules of positive work on it, so I add 600 to 400, I get 2,000 joules. And we're going to learn in the next class how to turn that into its velocity value, not hard. Okay. Now, what if it was a slope then? What if it started with a large force and the force got small? Well, we've done this before. I'm just going to say 300 I'm going to say 300 times 8, and I'm just going to divide it by 2 because it's half of that. So 300 times 8 divided by 2, that gives me 1,200 joules. And again, if it started off with 400, now I've increased it by 1,200, it has 1,800 joules worth of energy. Really straightforward. The one thing you got to keep in mind, though, is positive force means it's acting in the direction of motion, means it's going to cause the object to gain kinetic energy. But what if we have a negative force? Okay. So let's just say that I have an object that initially has 1,000 joules of kinetic energy. Now we're assuming it's moving in the positive direction. All right, whatever direction it's moving, we're going to call that positive. This force is acting against that in the negative direction. So it's going to do some negative work here. I'm just going to integrate to find out how much negative work. I'm going to say negative 150 times 4. That gives me negative 600 joules worth of work done. If the object started off with 1,000 joules, well, I've just taken away 600 joules from it, so it now has 400 joules worth of kinetic energy, still going in the positive direction. But it doesn't have to always go in the positive direction. So watch this one. Let's say this object initially had 400 joules worth of kinetic energy. I integrate to find the area under the line, and so I get negative 200. That means the force was applied against its initial motion. 200 joules. 200 newtons times 3 meters. So when I solve for the work, I get negative 600 joules. And if I apply that to its initial kinetic energy of 400 joules, I get negative 200 joules. But wait a second. We learned there's no such thing as negative energy. And that's true. There's negative work, but there's not such thing as negative energy. And so that negative work just means I was applying the force against the direction of its initial motion. So what happens is this. I would just say, well, it ended up with 200 joules worth of energy, but traveling in the negative direction. And it does make sense because look at this. All right. So what happened was at first it was going, remember, it had 400 joules. I applied negative 200 across 1 meter. I just took away 200 joules from it. Now it's got 200 joules. I took away another 200. Now it's got 0. At this point here, it stopped. I did enough negative work to bring it to a stop. And this last 200 joules was basically taking it from rest and making it accelerate in the positive direction. And so it had 200 joules worth of kinetic energy just going the other direction. So remember, there's no such thing as negative kinetic energy or negative energy at all. Sorry, this looks like a mess. That's my bad, okay? But let's just look at this. What if we had to do it algebraically? Say, okay, look, I've got a graph. I have a 20 kilogram mass that's traveling initially at 10 meters per second, and I have a graph like this. I want to find its final velocity. Sometimes they do ask you to calculate these values, and you just have to be able to apply work and kinetic energy. Let's just look at this here. So the first thing I do is I'm going to say, well, work in a force versus distance graph is the area under the line. Now let's just find the area under the line. I have 100 times 10, that's 1,000, okay, plus 100 times 10 divided by 2. So when I add that up, I get 1,500 joules worth of positive work that is done. Now remember, work equals change in energy. The energy in this question, in this case, is kinetic energy. That's the only one I've talked about yet. So delta always means final minus initial. So the work that was done which is 1,500 joules, is going to equal the final kinetic energy minus the initial kinetic energy. Now, how much kinetic energy did I start with? What was my initial kinetic energy? Well, my initial kinetic energy would be 1/2 mv squared. So 1/2 mv squared, that gives me 1,000 joules worth of kinetic energy I started with. Okay, so I'm going to go back to this here. I'm going to say work equals K final minus K initial. Work was 1,500 joules, which we got from area under the line. We're looking for K final. Well, we're looking for final velocity, but we're going to get it from K final minus whatever its initial kinetic energy was. And what I find then is the K final is 2,500 joules. So if I know the K final is 2,500 joules, I'm going to say, well, K equals 1/2 mv squared. So I just put 2,500 here equals 1/2 mv squared. And when I solve for phi, I get 15.8 meters per second, which is faster than what I started with because I did positive work. Thanks for watching. That's all I got for you. See you tomorrow.